Hi, very good afternoon to all the students. How are you today? So I hope you all are fine. I can see many of you have already joined the Google Meet session, including 28 of you. I can see Boon Kyung is here, Chai Siu, Chu Ye, Chun Wei, Chong Yi, Han Xiang, Han Dong, Xin Shen, Jing Wen, Junming, good afternoon, Chong Yi. Kashing, Chong Yi, I just observed that you have joined the old link, right? Usually we only have the old new link like 15 minutes before the class. So sorry if you join over the other class. Yeah. Okay, so okay, I can see Ken Sing, Kashing, Brenda also here, Maylin, Ernest, Tiang Le, Wei Hong, Wen Yang, Wen Liang, and Xu Pian, Xue Wen, Yan Chang, Yao Ting, and Yi Hang, Yi Si, Yong Chuan, Yu Yang, Zelim. Okay, most of you have already joined. I think only maybe 2 or 3 still coming in. I hope they will come in very soon. So basically, for today, we are going to continue our lectures on the pipelining. So this lecture on the pipelining, we have already done in chapter 3, but for this chapter 4, we are mainly to deal with the hazards that might caused by this pipelining. Okay, so before I start my class, any things that you want to ask me regarding this subject? Any problem you face? Anything you want to ask? I can see one more joining. Yeah. Okay, almost 30. So for your information, for this Friday, we don't have class. Yeah, we usually we have 1 hour class, right? But we don't have. So we are going to replace this at the later time when we need to do the presentation for your assignment. Then we might need more times. By that time, you will do some replacement. But if before that, if we need to replace some classes, I will discuss with you to find a suitable time. So what time will you be suitable for you to do the replacement of the class? Can I get some opinion from you? Maybe Chia, do you have any suggestion? Chia or anyone? Jingwen? But Jingwen is the contract for RTE itself, right? Any suggestion? When is the best time to do the replacement of the class?
Sir.
Jingwen, yeah.
Yeah, I'm Chie here.
Yeah, Jingwen. And when we are Chie here, Chie also talking. Chie, when is the best time to do replacement?
I think will be on Wednesday and Thursday.
Wednesday and Thursday. What time? Which slot will be more comfortable for you?
For Wednesday, 8 a.m. until 12. 12
time.
Sorry.
That time will be available for all of you.
Yes, correct. From 8 a.m. until 12:30.
Oh, okay. How about Jingwen? Jingwen, are you free on Wednesday?
If you're talking about the same time slot that PA proposed, that will be 8 to 10.
I could not hear a voice, Jingwen. Okay, type if you cannot.
Okay, never mind. Can you hear me now?
Yeah.
For the time slot, TA mentioned I'm only free by at 8 to 10.
8 to when?
10.
8 to 10. Oh, then should be fine. If 8 to 10, then we will make our replacement if necessary from 8 to 10. So there will be no problem. Do you have any class after today 4 p.m.?
Not for me.
Not for you, not for Jingwen. How about GS?
Yes, we have a lab until 6.
Is it for every week?
Yes, week 3 until week 10.
Oh, week 3 until week 10. Oh, that means if we want to do the presentation after week 10, it's still possible for the Tuesday, right? For today, right?
Yes, correct.
or then we can extend from the Tuesday, then will be easy for you so that just continue from there. Yeah, but we will discuss about this later. Okay, so thank you for your for your opinion. So I will arrange the class if needed on Wednesday morning 8 a.m. or 9 a.m. 8 a.m. is too early I understand that most of you still want to have some rest in the morning. Maybe start by 9 also if not urgent we will see how okay. So don't worry. So basically for today we are going to discuss about the pipeline. So without further ado, we already have 29 students joining us. So there are still 3 of you haven't joined yet. So we will start to do the pipelining. Okay, let us start. So basically, this is the chapter about the pipelining. There are 3 types of the hazards that exist in pipelining. The first one will be the structural hazard. Okay, structural. Okay, structural hazard. The second one will be the data hazard. The third one, what is the third one? Can anyone tell me what's the third one?
Control
After
hazard.
the data. Yeah, pardon?
Control hazard.
Control hazard. Very good. Please give a big round of applause to your friend. Okay, very good. Control hazard. Yeah, you're right. Control hazard. Okay, later we will see. Okay, for these 3 types of hazard, actually is the hazard, or we call it danger, that can occur when you do the pipelining for the computer. So for today, we are going to discuss the second type of the hazard, but let us do some revision on the first type of the hazard. What is the structural hazard? Okay, a structural hazard is basically because both of the instruction, we have 2 micro instruction, 1 and micro instruction 2. They basically want to access to one resources like ALU, memory. Okay, so it has caused a structural hazard because in the computer structure, it does not support, it cannot use, it does not have 2 ALUs for your computers. Okay, so it will cause the structural hazard when 2 of the micro instructions access to the same resources. Resources include the ALU and also the memory. Okay, so this is for the structural. So today we are going to learn about this data hazard. As the name mentioned, the data hazard occur because both of you want to access to a same data. For example, maybe the register number 1 or register number 2. Okay, so you have 2 micro instructions, but both of them want to access to this one of them. Maybe they want to access to R1 and R2. So this occur when it occur because when anytime there are instructions active that need to access the same data location. For example, if you have the instruction A and the instruction B, and the B manipulates data before the A does. Okay, so this violates the order of the instruction. Okay, since the architecture implies that A completes entirely before B is executed. For example, let's say I want to have this move. I have to, let's say I do this move A, H to H. This is my favorite. And then you have another instruction, add AH 1H. Okay. In this case, the AH in this the result of the AH here, originally it should be AH equals to 2H plus 1H equals to 3H. However, when you add the AH into 1H, so you must complete this one first. So A must be completed. A must be completed before the B started. Okay, before the B started. So using the pipelining, you might have the problem. Why? Because let's say you have the SPI stages over here. Okay, so you have the two instructions. So instruction fetch is the first one, instruction fetch. Then instruction decode. Okay, ALU, right? And then the memory access and also write back. This is for the first instruction. Okay, for here, the write back will only occur at the cycle number 5. However, for the second instruction, okay, over here, let's say you have the second instruction over here. You will do the ALU and the data fetch instruction decode when you need to do it at these 2 cycles before even the first result has been written back. Okay, so in this case, you are using the old AH. The AH value might not be correct when you do the addition. Yeah, so that's the problem about this data hazard. So this violates the order of the instruction, since the architecture implies that A must be complete entirely before the B is executed. So this is about the data hazard that might occur. So how do we solve this problem? We can solve this problem if we have the, like what we did last time, we put some, if we put a little bit bubble before we started everything. Okay, of course, some might start over here. Instruction fetch might, maybe you can fetch the instruction first. Okay, so after that, only you will going to do the instruction decode, address calculation or ALU, and write back, memory and write back. Okay, this will actually solve your problem for the data hazard. So do you have any question about this data hazard before we continue and finish this chapter by today? Then we do the tutorial. If we have time, then we can discuss a little bit about assignment. Any question? Yeah, any question from anyone? Let me see the chat box. Yeah, no question. Okay, now very good. Now we continue. Yeah. By the way, this is the last class. Oh no, for the group number B, we still have one tutorial class on Thursday afternoon. We will just continue with the class, yeah, because it's just everyone is staying at home, right? Yeah, so we can complete the class. Then before we go for China CNY dinner, then you will be feeling more relief, right? Yeah, so we don't change the class on Thursday. Yeah, is that okay for you?
Okay.
Yeah, okay, because it's just 1 p.m. right? Nobody eats so early, right? But if you eat, I don't mind if you eat while you listen to my lectures or tutorial is fine. Yeah. So, never mind. Okay, next. So we have the data hazard. So the execution order say that the instruction A must be completed before the B can start it, or instruction I must be completed before the instruction J. So this is called, how do we call this data hazard? We say that read after write, RAW. We must read after we write. In the previous example, for example here, the instruction J might try to read operand before instruction I write it. So in this case, you can see that they want to add R1 from R2 and R3. So R1 is equals to R2 plus R3. Okay, R2 plus R3. So in this case, the R1 must be computed first before we move into the instruction J. Then we can calculate R4 by adding R1 and R3. So we have the R4 equals to R1 plus R3. So in this case, we can say that it's caused by the dependence in the compiler nomenclature. Okay, so this one is what is the meaning of this nomenclature? The meaning of this is the naming. Okay, the way to name something. Okay, let's say if you want to give, they have some way to give the name. So it's nomenclature. So the hazards actually basically results from an actual needs for the communication. So that means whenever you face this problem, so you must have the completely 5 micro instruction completely executed, then before you start a new one. Of course, you can start the instruction fetch first, but it depends on your architecture. So if you put a bubble over here, if you put a lot of bubbles, you will be able to avoid the data hazard. So this is called dependence. So J dependent on I in order to be run. So this is for the rate after run. Any question? Anyone want to ask any question? Okay, you know what? Then I will quickly go faster. Yeah. Any question? We start not at oh yeah, you're right. Tiong Le, you're right. You have a very good observation. It's a sub R1 minus R3. Yeah. Okay, Tiong Le already observed one discrepancy here. Yeah, you're right. Okay, this is a big drop off to Tiong Le. So so that he can observe this. That means he listened to the class very carefully. Okay, very good. Next. Okay, now the second one is right after the read. So instruction J, try to write operand before the instruction I, read I. So it might get the wrong operand. So you can see here, the subtract R4, R1, and R3. So R4 equals to R1. This time we are right, minus R3. So here R4 equals to R1 minus R3. Now, you want to add this, okay? Add the R1 equals to R2 plus R3. Here, so the instruction J try to write operand before the instruction I, read the I. Okay, read the I. What does it mean? If you subtract, so if you try to do the J, okay, so this is called anti-dependence by compiler writers, the result from reuse of the name R1. Okay, now you can see, when you want to do this, you must write after read. Okay, you must do the, okay, you see previously we have the read first, then only after the write, right? Okay, read only after writing the first instruction. Okay, here you write, then only you can read here. So basically, instruction J try to write operands before instruction I, read the I. So again, the wrong operands. Okay, so here you can see subtract R4 equals to R1 minus R3. Okay, then R1 equals to R2 plus R3. So might be, if you have the pipelining, so R1 might be, this one may be read first. Okay, maybe write first, written first. Okay, written first, then only R4 we go and access this one later. If this happens, we can say that we have the write after read data hazard. Okay, you write after read. Okay, so you only write it after the read. Okay, so you have this data hazard. So that means we have the problem with this pipelining. this can only happen if you have the pipeline like this. Let's say you have the two threads together. Let's say people, they want to do two together. This one is a very powerful pipelining. So 1, 2, 3, 4, 5. Maybe you have different micro instructions. So if both of them, actually I and J, they do get it together. But in mathematics, we must do this one first one, then only we can have the second one. That's why. So because of this, then maybe they do the second one first. Okay, so this one they run first, then only they run this second. In this case, they will cause the data hazard. Okay, so this is called the right after rate. Right after rate. Any question? Right after rate, yeah. So they write, you must write it after you read it. Okay. After you read the R1, then only you are allowed to write. So they say, please, here, this is should write after read, not otherwise. So you write anything here, don't write this before you read, before the eye has a chance to read. Yeah, you must write let the instruction eye to read first, then only you write. That's why I say write after read. But it will be very strange because it can't happen in the mixed 5-stage pipeline. Why it can't happen over here for the mixed 5-stage pipeline? Because the mixer, in the mixed pipeline, all of them are separated. So this is a mix. For the mix, there are 5 stages here, right? So all the instruction can only be executed after one another. Okay, after the I only you have the J. So in this case, right after read, data hazard will not happen in mixed 5-stage pipeline. So mix has very good in handling this data hazard for the right after read, but not read after write. So in the first case, the read after write can still happen in mix. Okay, any question? I can see Chie has an eye. Why Chie eyes is dot here? Okay, very good. So, okay, if no problem, then we continue because we still have a lot of hazard. Then later, when we do the tutorial, then you will be able to study well. Okay, now we have the previously right after read. Now we have one more terms we call right after write, which is the W. So execution order is still like this. Instruction I, after that instruction J. So they say that instruction J try to write operand before instruction I write it. So leave the wrong result. So in this case, okay, we have the sub R1, R4, R3. So R1 equals to R4 minus R3 for the mixed instruction. Now, we have another instruction also calling R1 equals to R2, okay, minus R3. Sorry, this is add, subtract, and add. So in this case, this one must be executed first, then only this. But however, for some of the pipeline system, it can actually run these two together. So it might run this one first, then only you run this one. So this will trigger the data hazard. Okay, in this case, when you do the next instruction, multiply R6, R1, multiply R7. In this case, you will get the wrong answer. Because we know that from mathematics standpoint, first instruction must be executed first before the second instruction. So this one we call it output dependence. Okay, there's a name for it, output dependence by compiler writers. This also results from the reuse of the name of R1. So now we have the right after right. Yeah. Okay. This also can happen in MIPS 5. Why? Because for MIPS 5, we have the pipeline like this. Oh, why? Okay. Now we have the pipe. Right after may not happen using only happen for the other types of the pipelining where, okay, what happened is like this. They're together. The pipelining do together. There are two pipeline together. So it can happen for this right after right. Okay. So all instructions take the 5 stages and rights are always in stage 5. So we will see the right after read and right after write in later more complicated or pipelining. Okay, you already learned 3 things: read after write, right after read, right after write. Do you have any heads up when you have the read after read? Let me ask you: will it be read after read hazard? Think about it. Will it be? Let me do some pool. Okay, let us see. Is there read after read hazard, data hazard? Okay, answer is very simple, just yes or no. Okay, I will launch a pool. Please answer. If you cannot access to the pool, please use the chat box. I have started to see 3 answers. They're very fast. That means everyone is very focusing on this topic. Most of you answer, yeah, 2 minutes. Okay, I'm going to end the pool in 10 seconds. Okay, 5, 4, 3, 2, 1. Okay, 0, we end the pool. Okay, you can see the results. So here, most of you has already guessed no. Yeah, I can see most of you guess no. We don't know whether it's correct or not. Later we will see in later. Okay, so you can see in this pool. So let me see the result. Yeah, Chung Yi, any question?
Actually, no, but
Okay,
I don't know why it show the symbol.
Which symbol? Oh, you already muted, but they never show the mode mute. Okay, never mind, it's okay. Yeah. So yeah, then never mind, it's fine. So no, mostly answer no. Yeah, very good. Please give a big round of applause to all the friends. Okay, most of you have already answered no. Okay, very good. Let's see the answer. If let's say later I see read after read, then okay, let's see. Oh, no more. That means there is no read after read. Because using common sense, if you read first or read later, if you don't write, as long as you don't write, then it won't cause any hazard, in my opinion. Okay, I think it should be correct, because you read only, right? You maybe today you read the newspaper, tomorrow you read the newspaper. So no matter who read first or who read later, so it will not cause any hazard, right? It's still fine, right? So that's what my thinking. So that's why we only have read after write, write after read, and also write after write. Okay, so how do we solve the read after write? What we do is we can use the hardware to detect the read after write, and then we store. Okay, so this is what it means that store. Let me tell you what is store. So we have 5 stages over here. If you want to store, that means you can actually put some bubble over here. So here you put some bubble. Usually we don't need to store the instruction fetch. 1, 2, 3, 4, 5. So you put some bubbles here. So you store. Store means you stock it. Okay, store, total store. So assume the register return then read each cycle. So you can assume that register return then read each cycle. So this one is low cost to implement, simple. Reduce the instruction per cycle. Means you assume the register must be read first, must be written first, then only you can write. So no matter whenever you need to write the register, you write first, then only you read. Okay, so this is the way to solve the read after write, and try to minimize the stores. Okay, this way you can minimize the store. But to minimize the store, read after write stores, you can use the bypass, forward, short circuit. We use the word forward. So you can forward the data. What does it mean by forward? Let me tell you. Let's say you have the data over here. So you have this one. This one is the ALU, right? Yeah, this one is what? Let me draw again, because this one already solved using the store. So let me tell you how to do the forward. Okay, for the forward, this is the original MIPS. How can we do the forward? Okay, this is ALU. So forward means, sorry, this is ALU. Forward means this is calculation, this is ALU. Okay, forward means you actually can bring this data to your second pipeline directly, go into this ALU. You do not need to wait until write back. Let's say this one write back, move AH2. This is my favorite instruction. Add AH3. Okay, so you can actually get this one. This one already got the 2H, right? But you haven't written yet, right? So don't wait for it to read. Okay, you hear you write back, right? You have to wait until this cycle, so you're late already, right? What the pipeline do here is to forward. So we forward the data needed directly to ALU from the second pipeline. Yeah, this is called forwarding. Instead of store, we use the forwarding. So when you do the forwarding, you will be able to minimize the stores. Okay, of course, the source is the best solution. If you stop everything, wait until you finish, then only we start, then it will be better. This one forward, cannot, but very complex. Yeah, very complex. So you have to wait. You have to let the ALU give to this ALU. So you must be having very, very good designer so that you can design like this. If not, then the store will give you the very best result. Okay, now use the data before it's in the register. So before the AH has already this 2H. So it will reduce the stores, because stores will spend you like at least four cycle. But if you do the forwarding, there's no cycle loss. Okay, but it's very complex. Not all the computers can handle this. Yeah, it's crucial for the common RAW hazard, read after write. So the best instruction, best way is still the store, so you can solve the problem. But forwarding can, but it must have a very good designer for this one. Yeah. Okay. So any question? Okay, if no question, let me run a pool. Yeah, I'm going to run another pool. Okay, let me ask you another question. Okay, I'm going to start a pool. Let's have to answer which methods can actually minimize clock cycle delay. Yeah. Which method you can start to do the pool. Okay, I see the first one already start to answer. Two minutes, yeah. Okay, still have half a minute. Okay, I will end the pool in 10 seconds, yeah. Okay, 5, 4, 3, 2, 1. I end the pool, yeah. Okay, this is the answer given by most of you. Okay, so let me go to the. Okay, we have the pool here. Very good. So most of you have already been able to answer. It's forward. Yeah, correct. You can forward the answer from the ALU or stage to the next ALU stage directly. So you will be able to save the time. So you will minimize the delay due to the clock cycle stock cycle delay. Yeah. So very good. This is a big round applause to everyone. Yeah. Okay, 16 more. Correct. Very good. Okay, now let's continue. Yeah. So thank you for answering. So we will continue. Okay, so we are going to talk further on the data hazards. Let's have a look at this data hazard. From here, you can actually see there are 5 instructions. Here with the add R1, R2 plus R3, R2 plus R3. Okay, this is for the first line. We have the instruction fetch, instruction decode or register, LU, memory, register. So this is the division of the stages, micro instructions. So now, what is the problem here? You see, they add the R1. R1 depends on R2 and R3, but R1 result only available during the end of here. right? You only get the result of the R1 over here. But here you can see all the instruction below here, all uses the R1. Nobody doesn't want R1. So all instructions want R1 to be appeared. So when they do this instruction based on the current pipelining process, so all these three and the fourth one all get the wrong result if you don't do any store or any way to solve it. So we can see that the use of the result of the add instruction in the next three instructions a hazard. Why is hazard? Because it gives you the wrong answer. You might think that the problem is not very dangerous because it might not cause you any dangers. No, it's very dangerous because inside the aeroplane, there is a microprocessor. If the microprocessor in the aeroplane designed by someone has this kind of data hazard, let's say if you ask them to fly to north, let's say fly to east, so you have the hazard. It will cause very dangerous consequences. So it's very, very dangerous for the real-time application. So that's why, since the register is not written until after all those instruction ready. So all this ALU here, all of them use the old data. This one I don't know because this one is after the instruction fetch. So instruction decode that take the register data after the write back stage over here. So that's why the last instruction, is that correct? It's still correct. This one's still okay but until the second to the fourth one is wrong. The answer definitely is wrong. So the last ones may be still okay, but it's no use because three results already wrong, right? So when whatever at the end also you get the wrong one, right? So it's hazard also okay. So this is the problem. So how we can handle this without using a store? If you store it, it's very easy, right? Everything store we just put here, then after that another one here. Everything is very well run, right? So it can run very well. But because to save the time, so there is unavoidable. So what you can do is to do the forwarding. Forwarding is a very good term. Okay, forwarding means that the result of the ALU can actually be passed to here. Then here it passed to here. All this can pass. So you do not need to wait to here to fetch the data, but you can directly fetch from the ALU. That means the ALU got a specific wire connect to another ALU, so it directly can execute them. So forwarding is the concept of making the data available to the input of the ALU for subsequent instructions, even though the write back hasn't gotten to write back in order to write the memory or registers. So in this case, if you do the forwarding, use the forwarding method. This is definitely a hardware method to design the computer so that it can forward, so it can solve the problem. So forwarding to avoid the data hazard other than the store. Store can also avoid with the high cost. Okay, but let's say if time is not a matter, let's say speed is not a matter, so store is still a very simple way, okay? Because for the forwarding, as I say, it's very complex, very, very complex. Yeah, it will cause many other design problem. Okay, it's not easy. Okay, so now the data isn't loaded until after the MEM stage. Okay, but if you do the forwarding, then you can solve the problem. But here, in this slide, they have another issue. They say that even though you do the forwarding, okay, even though you do the forwarding over here, what will happen? It will still cause a hazard. Why does it happen? Why it still happen? Okay, because There are some instances that the data isn't loaded until after the memory stage. Okay, so here the data only loaded after the memory stage. So in this case, it will still happen to have the hazard. Okay, so why? Because of the computer design, the design do like this. You only loaded after the memory stage. Okay, so and also instruction also same lah. So in this case, okay, so you can see load the word, load a data with the size of a word. So you add the R2 with the 0, then you put into this R1. But the 0 bracket R2 is a indexing addressing. Okay, index addressing means that R2 have to add with the 0. So in this case, this one only can be completed during this stage number 4, because you need the memory access. In this case, you only can forward here. So in this case, you still have to put some store over here, right? The forwarding itself may not be able to solve the problem. You still need to have some store here. Okay, store one store or 2 store before the instruction started, so that it can solve your problem. So the forwarding cannot work in all the ways, including the 0 bracket R2. This is called the index addressing. Index addressing definitely need a memory access. You need this one and also memory access. Because your bracket means memory access, right? Memory, right? If you have a bracket. Okay, now this is the 2 ways to solve your problem. One, you need a store. Other, you use a forwarding. Okay, now, in order to solve this, like what I say, the bubble or the store is necessary. So, because the forwarding can only happen after the memory, so it's better that you put some bubble at all the instructions, store everything. So, all stop, don't work anymore. Wait until the hazard finish. Then only they forward the data to the next ALU. That will be a way to solve it. Okay, so you can see that the memory access only happen at the stage number 4. So data forwarding can only happen after the stage number 4. So after that, you can actually forward the data from the memory access to the ALU. Yeah, so here we put a bubble. Never mind, because it's still, even though it's slower, right, but it's safe, right? So we don't have any hazard. But if you just continue to put ALU here, it will cause the hazard because you haven't completed right here, right? So you still want to calculate, cannot. Okay? Yeah, any question? Any question you can let me know, open your mic and ask me. Okay, no problem, then we continue, yeah? Okay, next one. The data hazard, this is another representation. Let's say if you don't like to draw a graphic, so you feel that drawing such a graphic, let's say people ask you to draw the pipeline diagram like this. So you don't like to draw, but you like to draw a table, figure like this, so you can still do this. So you can draw like this. So in this case, you draw a table like this. Okay, you got a table. So in this table, so you can put the instruction, then you put the instruction fetch, instruction decode, execution, memory, write back. Then you can do like this. Okay, let's say to solve this one has a hazard. Why this one has a hazard? Because the data only ready here. Okay, data only here, ready here. So even using forwarding, you cannot solve this because it haven't been completed. So if you do a store here, the data here completed can be channeled to execution for the second pipeline. So in this case, forwarding can solve your problem with the help of the store. Okay, if not, then it won't be able to help. If you don't use the store, no solution. So still have to lose one cycle. Yeah. So let us continue to discuss about this. So this is an instruction scheduled by the compiler. Remove the instruction in order to reduce the stop. Okay, so load word B to this register B. So code sequence is A equals to B plus 3 before scheduling. So if you let's say you don't have the cost to do computing, okay, to design a computer. Of course, we all are very small people. We buy a computer, then we just use it, right? We don't have any chance to design a computer yet. Let's say, so what we can do, we can actually use a good compiler. Okay, yes, you can see here. Load word RBB, load word RCC. So now you add the RA, RB, RC. In this case, this add RA, RB, RC have to wait. So you see, it has to wait for this to complete. So in this case, there will be a store occur here. You can see, right? For the pipelining. Also, same goes to here. This instruction have to wait for all these instructions to complete first. Have to wait. So you have to wait until the write back over here finish. But if your compiler is very, very brilliant, okay, they want to save you time. So what can the compiler do? We can actually load the BC, then bring forward the E. Then bring forward the E here. So that they do this one first. Then after you do this, these two already complete, right? Then only it will execute this. So no saw is required. So this is for the using the compiler method to solve this, to rearrange your instruction code so that it will not have any store. So this one is faster. Okay, this one is slower. Okay, any question? If no question, then as promised, we have about 15 minutes rest before we go into the second task. So I will continue later. Let me see when to continue later. 2:57, 3:12, 3 o'clock and 12. Okay, so 12, 3:12. So you come back by 3:12. Okay, so you can have your brunch or maybe a lunch dinner. Okay, so see you later. So don't worry, you have some enjoy some snack first, then before we continue. So all the best. So later I see you again in 15 minutes. Hi, very good afternoon to all the students again. So I think 15 minutes has passed so far, right? So we have to come back to the class. I can see that we have 31 students here. I think still have one absent. I don't know who is that. Huh? Do you know who is the student who has absent? Maybe he's using another device, which is not recorded here. I know that, never mind, later I can check, don't worry. I think maybe all of you are 31. Okay, 31, yeah. Okay, now let's continue to the last hazard. After we continue this hazard, then we can continue to finish the tutorial. So let's see what is this control hazard. Just now you have a friend who already answered this correctly. Control hazard, so give a big round of applause to your friend. Very good. So you have already done this control. You already know what is control hazard, right? Basically, a control hazard is when we need to find the destination of a branch and can't fetch any new instructions until we know that destination. Okay, so these are very different problems compared to the previous problem. Previous problem is because we want to use the same memory, or we want to use the same resources, or maybe we want to use the same data, same register, or we have the data dependency. You need to depend on your previous instruction data in order to get the new data. So this control hazard is a different issue. Let me do this. Let's say I have the move AH to H. Okay, now I have the compare. This one is not good. Not a good example. Why? Because he, even though, okay, let me do again. Okay, I still do the same thing. I move AH, okay, 2H. Now I do decrease, sorry, wait. Okay, what I can do? Okay, so I can subtract AH with the BH. Okay, now I compare AH with 5H. Now, jump equal, okay, jump equal or not zero, or jump 0, jump equal to, usually we don't use JE. Let me do it properly. Jump not equal, okay, jump not equal to a label, maybe a label. Okay, now we have another one, move AH by H. Okay, and then here we have the label. Okay, here we have the jump, we have the move BL3H. Okay, now if let's say you are a computer, so how do you execute the following instruction in the pipeline? You can see there are two possibilities that the instruction flow can be different. For the first one, if it's not equal, okay, so it can jump to label. The next one in the pipeline should be this. But if it's equal, so it can be jumped to here. So there's two possibilities. That's why we call it control hazards. Okay, how do you choose the correct pipeline so that the next one, here you have the first one, so next one can have your desired instruction. You want to put this one or you want to put this one? Which one? Which one will be better? So this is a very difficult problems, because as a computer you don't know, right? Yeah, you can never know which one is the right one, especially if you get the input from the user. So computer cannot guess. So it has to, they have no way to know. So you might get the wrong thing into a pipeline. After that, you have to delete it. Okay. So how do we handle this problem? Okay. So this is the control hazard on branches 3-stage store. Okay. When you have the branch equal, this is a mixed instruction. Branch equal to 36. If this R1, if that means if R1 equal to this R3, okay, then do what? Jump to 36, right? Label 36. Okay, so this is the meaning. Okay, so now the problem is I don't know whether it's equal or not. It can jump here or it can continue here. There's two possibilities. Okay, what can you do? Okay, in this case, let's say control hazard on branches 3-stage store. That means that they want to store 3 stages. Okay, they want to store everything until what? Until this one come up with the result. Then only you continue. So that is one of the way to solve the problem. Because you don't know which one for the next instruction. There's no specific next instruction. For this branch equal or jump equal, jump not equal, they they have to compare the data, then only they will decide whether you need to jump or not. So in this case, very hard to do pipelining. So that's why the best solution is still to store, but it's very slow. But if you store it, then definitely it's safer. Okay, yeah, no hazard anymore. So there are 5 ways that the computer designers have already taken or proposed in order to solve this problem. First, store until the branch direction is here. This one is definitely a very easy implementation and solve the problem, but it's slower. Okay, the performance will be slower, but it's very safe, no hazard. Now, the second one, you predict the branch not taken. So how do you predict? So you predict, you say that, I guess. Okay, I guess the branch not taken. So it will not branch. In this case, I guess it will take this. This is my pick, my guess. So if I guess so I put this one into the pipeline. So I guess something not taken, the next instruction into the pipeline. So this one is next instruction into the pipeline. So execute the instruction in sequence. So what if it suddenly branch? Then what can we do? Okay, if you branch, then no choice, then you have to squash everything, throw it into dustbin. So take out everything, then after that put the new one, new label inside. Okay, so this is advantage of late pipeline stage update. So C++ already calculated, so use it to get the next instruction. Means we guess first, okay? Then after that, if it's not correct, then we throw it. Then everything we log again. So this is a predict branch not taken. The third one is actually predict the branch taken. This one different. So this one, you just fetch the pipeline into the label instruction. Okay. So we assume that the branch will be taken. In this case, the next instruction will be the one branch. Okay, not the next instruction. Any question? Any question? If you have question, you can ask me. Shia, any question? Okay, I can see everyone has already untitled. Shia, no question now. Okay. Chungi, any question? Chungi, do you have any question about this?
The PC plus 4 is...
PC plus 4 is the next instruction address. Yeah, because currently, because this is, we assume that it's a 32-bit microprocessor. 32-bit microprocessor. In this case, it is 4 bytes. So for 32-bit microprocessor, the one address will be +4. That means in the memory is still 1 byte. Okay, 1 byte. Memory is 1 byte. So one instruction will take 4 bytes. 1, 2, 3, 4. So next instruction will be PC. This is PC +4. Yeah. Am I answering your question? Because for the 32-bit, microprocessor, they will take 4 bytes for one instruction. That's the meaning of the 32-bit. Yeah, correct. 1 cycle. You're right, Chung-Yi. So 64-bit, it will take 8 bytes. Let's say for some of you actually using 64-bit microprocessor, let's say Pentium i7. So you will be using 8 bytes for one instruction. Of course, you won't be using all the times, but the longest you can use is 8 bytes. Yeah. So very good question. Yeah, next. So now, the fourth solution is to execute both parts. Means I don't know how you execute okay, you have the pipeline. You see there are many ways. One is you can execute like this both parts. And unless you have a specific, you have 2 pipelines in parallel. If not, then you have to do this. This one is the next instruction. Okay, so this one is the label 36, label instruction. In this case, they execute both parts together. Maybe they have the parallel pipeline. If not, if possible, then they might have the parallel pipeline for their computer, so they can execute both parts. So anything if I control hazard, so you execute both together. It means you have to design a very sophisticated computer, extra set of the pipeline, extra set of the ALU, extra set everything. So this is how you execute the both parts. Okay, last one. Last one is about the delay branch. So delay branch is actually same. Actually, after I've done some research, delay branch actually is just like the predict branch not taken, about the same. Okay, in this case. So it's just like predict the branch not taken. So delay branch, you don't care anything until you squash the instruction after you have confirmed that it will branch. So the number 5 solution is delay branch. So one slot allow proper decision and branch target in 5-stage pipeline. So MIPS actually use this. Yeah. Any question? Okay, if not, then I continue. I don't want to waste too much time. So this is the control hazard. One very, very effective solution is to do the store. As I can say, you do the store, just that it's slower. The performance might be slower, but it will definitely save. And it's very easy to solve it. You don't need a sophisticated facility, resources, everything. Don't need. Okay, so you can solve your hazard. Okay, so this is a very good solution, especially for cost effective. You don't want to spend more money to design a new computer or design a more complex computer. Yeah, this is not easy. So the store will be the easiest way for the computer designer. Okay, so this is actually the data to show that how the pipeline speed up can happen for the control hazard, for the branch, for when the branch alternative happens. So due to the pipeline depth usually is maybe 5. Okay, 5. 1 plus branch frequency. Maybe branch frequency is 10%. It's not so much. Okay, maybe 10% is the highest you can get. Then branch penalty maybe 2 clock cycles. So in this case, you use this formula, you will be able to calculate the pipeline speed up. In this case, you can see that if you store the pipeline, you use the store methods, what will happen? You will take a very high penalty. Then your speed up versus the pipeline will be 3.5. Yeah, so this one is 3.5 times or over the 5 times is the maximum. So you take the predict taken. So you will have 4.4 speed up. It's slightly higher than the store. Then if you take the branch not taken, I don't know why, because most of the program actually, they do not take a branch. That's why they have the 4.5. I don't know why it does not take the branch. For example, they have the while instruction. So they have execute 1,000 times, but only the last time they will jump out of the loop, right? Yeah, so that's why in this case, the predict taken will be better than the predict not taken will be better than the predict taken, right? You see, you have the wow. Everyone learn C, right? C less than one, less while C less than 100, and then like this, right? Then C minus, right? Let's say C here equals to 1,000, right? Okay, for example, if you have this, of course, this is integer. Okay, so minus. Okay, in this case, the while always will not jump. The branch will not be taken until whatever. So it will always this depends on your design also. Later we discuss about this. Some argue this is jump, this is not jump. Later we will discuss about this. So with the delay branch, okay, delay branch, the penalty is lesser for some of the architecture. Okay, we have to see the computer architecture first. Then it will have the speed up of 4.6. Yeah. So this is for one of the test cases for the conditioner, and conditioner equals to 14%, was very higher. So 60%, 65% will change the PC for each case. Okay. So this is the case for this case. Okay. Any question? If not, then we move. So this is another formula. The speed up will be equals to pipeline depth, which is a 5 in our mix, and then pipeline store CPI. Maybe we can consider 2 store per instruction per 1 store. Okay, 2 store. Okay, clock cycles. So clock cycle and pipeline. Clock pipeline is, what's the clock cycle for pipeline? Maybe 100, and then clock cycle pipeline maybe 20, something like this. Then you can calculate. In this case, you will be able to calculate the speed up for your computer. Okay. So hazard limits the performance on computer, because when the hazards came, you previously assumed that your computer can function very well. Then when the hazards came, you have a lot of hazards in your programs. So what you can do is you can use the store. Then you can save you can avoid the hazard, but you will slow down your performance. So for the structural hazard, you need more hardware resources. Okay, you need 2 ALU or 3 ALUs, 2 memory access or 3 memory access. And then for the data, you need to use the forwarding, or you use the compiler scheduling. And the last one, for the control, you use the delay branch and prediction. Okay, you predict or delay branch. Delay branch, sometimes they have the different way to design. So when you study, do more research, then you know it's slightly different from the number 2, but it's almost the same. Yeah. So besides all this, what we can do, we can store. If you cannot do any of this, you just store. Yeah, just store the instruction. Don't let it to come in first until everything clear. This is how to handle the hazard. Yeah, unless you have a very sophisticated method, you can design, you have the resource, then only you design. Yeah. So I'm going to finish these chapters. For the instruction level parallelism, besides we are talking about the micro instruction now. how do we do the instruction level parallelism? What's the meaning of instruction level? For example, I'd like to use this example, move AH to H, move BH, BH, let's say BH, 5H. So if I have a computer, I want to execute this in parallel, then it might be faster, right? That's why in the computer nowadays, you have, for example, you have the computer, let's say in my computer, it's a Celeron computer, and 4000. So basically we have 2 cores, okay, 2 cores. In these 2 cores, you can actually split into the threads, okay, 4, 1, 2, 3, 4, 4 threads. So my computer here can execute 4 instructions together. This is called the instruction level parallelism. So they can execute these 2 together. This is called the instruction level parallelism. This has been commonly used since 1985 until today. Okay. This is pipelining. It's 1985. After that, we have the instruction level pipelining. Here, we look at extending the pipelining idea by increasing the amount of parallelism, exploited amount of instruction. Now we don't want to pipeline the instruction, micro instruction. We want to pipeline 2 instructions together. They come together, and then together also they do the pipeline. Okay, so it will be very fast, right? That's how the current computer doing. Okay, this start by looking at the limitation imposed by the data and control hazards, and then look at the increasing ability of the processor to exploit the parallelism. Okay, now, besides the instruction level parallelism, this one has to be implemented using this multi-core. 10 years ago, maybe 20 years ago, there's not much multi-core processors. But nowadays, everything is multi-core. Even though you have a Celeron, it's multi-core. Okay, multi-core is very important because, let's say for i7 computer, you can execute 32 instructions at once. Yeah, it's very, very powerful. So now, 2 main approaches to handle the pipelining. This one for pipelining, we come back. Don't think about instruction level. Now come back to the pipelining. So there are 2 largely separable approach to exploiting the instruction level. Still there, instruction level. Okay, we come back to instruction level. Come back here. Okay, exploiting the instruction level terrorism. There are 2 approaches. One is the dynamic technique. Okay, dynamic technique. Sorry, so we are still in the instruction level terrorism. For the dynamic techniques, what does it mean? You will redesign the hardware to locate the parallelism. So this one, if you want to do the dynamic techniques, so what you do, you split into multi-core. Multi-core. And then you can do multi-thread. So when you have a multi-core and multi-thread computer, then you design such a software, design such a computer, so you use the dynamic techniques. Or you can use the static technique. Static means you don't do anything, and then let the compiler to do it. So you must rely on the software. The compiler will help you. For example, you find that your instruction has the hazard, so you will rearrange your instruction in such a way that your instruction won't have any hazard, so you can execute faster. So this is software-based. But the practical implementation typically involves a mix. So they will use both of the methods because let's say if you want to design a computer, very difficult computer, so it might be a trouble, right? So if you want to design a very difficult compiler, also you will trouble. So what they do is they mix. Okay, some hardware will solve some problem, and then software will solve some problem. Okay. So this is a dynamic and static push to solve the parallelism. Dynamic is very hardware intensive. So it dominate the desktop and the server market. So for example, for Pentium, PowerPC, and Alpha, they use the dynamic approach. So the computer manufacturer will go and design a very sophisticated computer. Okay, whereas As for static, compiler intensive push has been broader adoption in embedded market. For example, IS64B and Ethereum. So this static that will depends on the server. Sorry, this one is a server IA64 and Ethereum. It depends on the software. So which one is better, static or dynamic? This argument, always got the argument when we talk about what is better, right? So it's required complex structure to identify independent instruction. So for the dynamic, you need to design a new hardware, you need high power consumption and low clock speed and high design and verification effort. And then this author actually they support using the compiler. Because using compiler, you can always save your costs. Okay, but this one is just opinion of one author. Some author might think that it's better to implement the sophisticated computer because software development also costs a lot. Yeah. So there are some argument. That's why it's argument there's no answer. You can either improve your computer or improve your compiler to do the parallelism. So there's no answer. My opinion is both also need to improve a bit. Cannot throw the task to one of the methods. Okay. So that's my opinion. Because I know that software also spend a lot of money to be developed. It's not easy. If you learn software engineering, then you will know it's very costly. Okay, that's all for this lecture. So if you have any problem, let me know. I will give you like 2 minutes to ask me any question. Any question?
Sir.
Yeah. Yes.
For the delay branch, I still didn't really get it.
The delay branch is quite similar to the number two. It's very similar. That means they will have the branch instruction. Then they do this. Define the branch to take place after following instruction. It's very similar to taking this one. Predict branch not taken. Okay, so it delays the branch. They don't branch first. Then they execute. Until they have a branch only, they will slot in. Yeah. So MIPS uses this. But in terms of implementation, the concept is the same. But in terms of implementation, there is a little bit different. So if you want, I can do some research, and then next time I will list down a little bit of the delay branch and different between these two, but actually very similar. Yeah, Chong-Yi, is that answering? Yeah, next time I will give you, because I already done the research, actually very similar. Yeah, except implementation. But the way they do is very similar. Later, I will give you the extra information. Yeah, very good question. Yeah. Okay, very good, Chong-Yi question. So now let's do the tutorial without further ado. Okay, we still have minutes. I hope we can do at least one question. Have we done the question number 2? Anyone can answer me? We have done. Yeah, we have done. Okay. Okay, question number 3. What is instruction level parallelism? Briefly define the following terms. Resource conflict. What is resource conflict? Okay, and output dependency. And then anti-dependency. What is instruction level parallelism? Okay, you can find the answer from the lecture notes. What is instruction level parallelism? So this will be the answer. Yeah. Okay, anyone can answer this? What is instruction level parallelism? Okay, resource conflict is more towards which one? Let me do a pool. Yeah, better so everyone can answer. Yeah, I will create a pool. Yeah. Okay, for resource conflict. Okay, refer to which hazard. Okay, let's hazard one, data, hazard, yeah, structural, hazard, control hazard, right? Okay, let's answer your question. I'm going to launch a pool. So please answer this. Resource conflict refer to which hazards? I've already give you a pool.
Sir, sorry for disturbing.
Yeah.
I'm here. Actually, by the way, the question two just haven't finished discussed. It's just halfway lah.
Okay. Later we will continue lah. We do this one first.
Okay,
Yeah.
okay.
Okay, Xie. Yeah, sure. Thank you for telling me. So now I'm launching the pool. So please do this. The pool. Please refer to the pool. Resource conflict. Okay, where's the resource conflict? Let's go and see the. Okay, where's the resource conflict? Mostly here, right? Resource conflict. Because you use the same resource for one problems. So resource conflict, setting up more resource. So what is the answer? Let's see here. Okay, this is the current 12 of you actually voted. Let me show everyone result. Yeah, 12 of you actually voted structural hazard. Yeah. Okay, answer is structural hazards, right? Okay, very good for those who answer correctly. Very good. Okay, next one. So let me structure resource. This one is output dependency. Yeah. Same thing. Never mind. This one I'll just talk about the answer if I do the full all the time, and then you will delay our class. Output dependency actually is the data hazard. Okay, and then for the anti-dependency also data hazard, right? Yeah. So this one you can actually refer to the lecture notes. Dependency, anti-dependency, it's right after rate. Okay. And then output dependency is here. It's right after right. Yeah. So these are all the terms you can actually. Yeah. Okay. So this is how you can answer. So sorry here actually I think it's a different question already. Yeah. This is A, maybe A. Yeah. This is quite different answer question. B. Okay. Now 3. Like what your friend said. We haven't completed this. Okay, what is the here? Calculate how many clock cycles you take execution of this segment on the simple pipeline without forwarding or bypassing. Now when we talk about this forwarding and bypassing, then you know, right? If I haven't taught this forwarding to you, then if you do this tutorial, it's very strange. What is forwarding? What is bypassing? After listening to me for 2 hours, now you know what is forwarding, right? When the result of the branch instruction, a new PC is available after the write back stage. Show timing of 1 loop cycle in figure 1.1. So this is figure 1.1. So what is the solution here? The solution here is because, okay, so how many clock cycles? So you have to draw the proper pipeline. This is a pipeline, okay? So you can see, you execute like this. Instruction fetch, instruction decode, execution, memory access, and write back. Second one also same. So there's no problem with this. No problem, right? This one R1, this one R2. Okay, this one is index addressing. R4 added to this 0. Okay, they get the content from the memory according to R4 address. Then this one add 0, this one add 400. So difference between this, I think it's a difference between this is 400 lah. Okay, depends on how the instruction execute. So third one, the R3 actually depends on the R2. Okay, so one of my students actually teach me with the Windows Shift S. Yeah, let me see. This one, how I use this. Windows need. Yeah, just now got a student teach me this. Windows need, face need, full screen sneak. Okay, window, right? So I can sneak here, right? Okay, you can see here. Yeah, add integer R3 equals to R1, R2. So what can you see here? This is the snipping tool. Okay, yeah. What can you see here? You can see that these two instructions, basically, they will need the result from these two. Because you load the data for R1, register 1 and register 2. Now you add the R3 need to wait for R1 to R2 to be completed. So you only can read after write, right? Right, read after write. Yeah, read. You can only read these two after you have write. This is a read after write problem. So now, the first one and second one, no problem. Now second one come with the problem. The third instruction fetch, decode. Now calculation or address calculation. So in this case, these two haven't been written. You can see these two haven't been written. Which two haven't been written? Okay, so which two haven't been written? These two haven't been written. So as you can see here, these two haven't been completed. So you cannot get the data from right back from here. R1 and R2 hasn't been calculated. Okay, so we will put the store over here. Then the execution only happens after these two has completed. So we have this. Now, of course, the next one I have to follow because the previous instruction also haven't completed. Why you want to be so fast, right? Also delay together. After that, you have the store over here. Then here, store word. This is load, this is store. You store the word of R3 based on the R4. In this case, no problem. But here you can see, no problem, even though no problem, but why you want to delay the write? Why you want to delay the write? Anyone can answer? Why do you want to delay the write? Because here, R3 here got problem because you cannot write the R3 before the third instruction R3 is written. Okay, remember you can only write the fourth instruction R3 after the instruction has been written. So this is called the write after write problem. Okay, write after write problem, that's why they do the one store over here. Okay, then only you will access the memory and Okay, so here, the last one got what problem? The last one is actually branch not equal R4. This one R4. But R4 have to wait for this one to complete first, right? Right after, right? Huh? After this instruction 5 return the R4, then the last instruction can use the R4, okay, here. So that's why they also have this store. Then we get this. So in total, you can execute this in 15 clock cycles. Yeah, any question about this? Yeah, I believe many will have question. It's quite a very complex one. After you listen to the lecture, I believe you have some ideas. Any question? Question 2 haven't been finished discussed. Yeah, we are discussing right now. Anyone has any question? Okay, then we know that the number of cycles in the loop is 15 clock cycles. So number of clock cycles for a segment executed on pipeline processor is 160 plus number of clock cycle in the loop L1 multiply number of clock cycle equals to 1 plus 15. Okay, multiply 400 divided by 4. Okay, 400 divided by 4. Because you have to branch 400 times. Okay, so divided by 4 times, 100 times. So each time you have to take 15 clock cycles. Okay, take 15 clock cycles. Then that's why. That's why you have to have the 1 plus 15 multiply 100. It's 1501 clock cycles. So this is the okay. Yeah, 15 clock cycles. Okay. So you have here, so you can see how many clock cycles. So 15, 15 here. That to execute all over again. This is the one instruction fetch for 15. 1, 2, 3, 4, 5. Okay. Yeah. So any question? Okay. If no question, then we can continue. Load the 4. This one. You look back, the L1 is actually here. Look back here. So 1 over here, if stage of the initial instruction. Initial instruction over here. Yeah. So first one, so you have to have the instruction fetch. Okay, then it will look again. Okay, any question? So if not, then we go to the last question. Speed up of the pipeline processor compared with non-pipeline processor. Number of clock cycle for the segment execution on the non-pipeline over the number of clock cycle for the segment execution on the simple pipeline processor. So for the pipeline, we have 3005 over the 1501 for the pipeline. Where we get the 3005? How do we get 3005? Okay, 3005 is because we have this one, everyone 5, right? 5 multiply 5. Okay, and then multiply the 100. Yeah. So you can get 3005 3005. This is 1005. 3005. Okay. So 3005. This one is originally is 3005. Yeah. Clock cycles. 1, 2, 3, 4, 5, 6. 6 multiply 5. 6 multiply 5. Multiply 100. Okay. Let's see. What's the answer here? Okay. This one, 3005 is actually 6 instruction. Original instruction. Multiply 5 cycles. Multiply because it has 1000 loops, right? Oh, sorry, 100 loops, right? Also plus first instruction plus 5 first instruction okay, so plus 5, so you get this 3005. Okay, for the non-pipeline you need 1501 as calculated over here, so they will just look like this. Yeah, any question you have? I think we still have 3 minutes only. Yeah. Any question before we end the class? Actually, I want to continue, but I know you have a lab, right? Do you have a lab later? So far, so good. Yao Ting say, so far, so good. Today, you never say anything, right, Yao Ting? Okay. So, okay, it's no problem. Because I understand you also have a lab, so I don't want to drag you so long. So thank you very much. And please do other questions at home. So for group 2, I will still see you later on Thursday. Yeah, Thursday we will discuss tutorial 1. There's still a few questions for us to discuss. Then after that, you can celebrate your CNY. But please stay at home and try to avoid going out so often. So, and all the best and happy Chinese New Year. Okay, thank you. You may leave now. Thank you very much. If you have no question, happy CNY, chào Yao Ting. Okay, bye. You're allowed to leave now. Thank you. Thank you. Thank you, Yao Ting. Thank you, Xu Bian. Thank you, Tiong Le. Thank you, Melina. Thank you. Happy Chinese New Year. Chia, Wen Mian. Bye. Okay, bye. Okay, thank you. Thank you. Ding Dong, can sing it. Okay.